Imagine a highway. It is a few hundred miles above your head. It is invisible. On this highway, vehicles travel at 17,000 miles per hour. Each vehicle is a satellite. It does a job. It helps you find your way. It shows you the weather. It connects your phone call. Now imagine one of these vehicles breaks down. It becomes a ghost car, drifting across every lane at incredible speed. This is the reality of space today. We have not yet mastered the art of cleaning up after ourselves. One collision creates a cloud. That debris causes more collisions. A chain reaction could make orbits unusable for generations. Ahead, the baseline physics, then the ripples on Earth, insurance, law, inequality. The feedback loops that escalate risk, and how a smarter standard can harden the system instead of breaking it. The visible problem is space debris. We see a growing cloud of junk. This junk threatens active satellites. Preventing more junk means deorbiting at end of life. Burn up safely, away from people and assets. But focusing only on objects misses the system of decisions that puts them there. A rule changes not just counts, but behaviors, how teams build, launch, operate, and retire. A standardized deorbit rule creates new pressures. It adds costs. It adds technical complexity. It creates new requirements that must be met. Do operators build more robust satellites, or cut corners elsewhere to afford deorbiting? This is the hidden part. Not just physics, but economics and incentives. A poorly designed rule can concentrate risk where we least expect it. We start with the facts, satellites and the immediate effects of failed deorbit, then second-order consequences, insurance, law, global inequality, and the loops that escalate risk. Think like an engineer. Where are the stress points, what fails, and what redundancy prevents collapse? The goal is a standard that cleans up space without creating a new crisis. Keep the space highways open and safe for everyone for decades. Next, when things go boom, the first-order physics that set the stakes for everything that follows. Let us begin with the basics. Low Earth orbit runs from about 100 to 1,200 miles up. It is the busiest part of space. Satellites move around 17,500 miles per hour. At that speed, even tiny objects carry enormous energy. A fleck of paint can chip an ISS window. A 1-centimeter sphere hits like a bowling ball dropped from 5 stories. A defunct satellite is much larger. It cannot maneuver. It cannot dodge. It just drifts. A failed deorbit turns a satellite into debris, joining tens of thousands of tracked objects and millions of smaller pieces. Its presence increases collision probability for nearby orbits. Agencies track, warn. Operators burn fuel to avoid, shortening mission life. Debris imposes a cost on everyone. In 2009, an active Iridium satellite collided with defunct Cosmos 2251 at nearly 26,000 miles per hour. Over 2,000 trackable pieces were created. In 2007, China destroyed Fengyun 1C, creating over 3,000 trackable fragments. Much of that debris is still in orbit today. These are first-order effects. One failure becomes hazard. One collision multiplies the hazard for everyone. Quick pulse check. Tap like if clarity helps you think. Drop a comment with a risk you think is overlooked, and subscribe for more grounded what-ifs. Your input steers the next investigation. The consequences do not stay in space. They ripple downwards. As risk grows, premiums and operations costs rise. Extra fuel adds weight, which increases launch costs. Or operators shorten mission life, driving more replacements and long-term costs. Costs pass to consumers, navigation, communications, connectivity. Wealthy actors afford resilience. Smaller firms and emerging nations get priced out. Some orbits become inaccessible to those who need them most. The benefits, agriculture, disaster response, education, slip away where they are most needed. If one country's satellite damages another's, who is liable? Old treaties are vague. Disputes strain diplomacy. In a brittle geopolitical environment, a space incident can escalate fast. Space debris is technical, economic, social, and political. Its ripples land on the ground. Next, the loops. how rising debris risk pushes behaviors that create more risk, and where a single shock triggers a cascade. Complex systems are full of feedback loops. Some balance, some reinforce. Space debris is dominated by a powerful reinforcing loop. High-value operators add shielding and fuel, making satellites heavier and costlier. Others respond by building lighter, cheaper satellites, cutting redundancy, shielding, even deorbit quality. Those cutbacks increase failure rates, feeding the debris loop. Systems absorb small shocks until a threshold is crossed. A single catastrophic collision with a large derelict could jump the risk, a step change, not a slope. Thousands scramble to dodge, many succeed, some fail, cascading into more debris. Outages cluster over weeks, comms, navigation, Earth observation. This is not science fiction. It is plausible once primed by reinforcing loops. If our controls ignore these dynamics, they may fail at the very moment we need them most. When the cure becomes the sickness. If a standard dictates a specific technology, the whole industry depends on one supply chain. A defect, embargo, or factory shutdown can ground fleets, or worse, fly flawed hardware. That creates correlated risk, a single point of systemic failure. Robust deorbit systems add mass and cost, hardest for startups, universities, developing nations. To cope, some choose cheaper launch or cut testing, shifting risk, not reducing it. Rigid rules chill innovation, even when better, cheaper deorbit ideas emerge. Deadlines can trigger launch rushes. Jurisdiction gaps invite flags of convenience. Instead of solving the problem, we export it. So what if we get it wrong? The future slows and becomes fragile. Orbital gridlock. Valuable LEO bands become unusable. Launches thread Russian roulette paths. Insurance costs become astronomical. Commercial innovation stalls. Access narrows. Space skews more militarized, exclusive, less accessible. Services degrade. We overbuild terrestrial backups, costly and less efficient. Not fireballs, just a quieter future of lost potential. A cosmic tragedy of the commons is the default if we fail to design wisely. It is not inevitable. We can think differently. Design for resilience, not just compliance. Here is the deeper payoff. Make the rule performance-based, not prescriptive. Encourage diversity, chemical, electric, drag sails, tethers. Mandate redundancy, belt and suspenders, so single failures don't strand satellites. If one tech falters, the system stands. Fund a multinational tow truck to remove the most dangerous objects early. Test rules for hidden loops, bottlenecks, and perverse incentives. Nudge thousands of actors towards safer choices. The sky is a shared resource, dump or garden. The choice is ours. What scenario should we explore next? Share your ideas below. You've been watching Ifverse, where imagination meets possibility. See you in our next reality.